So 6.5b takes us through another growth model. The most famous kind of growth model is exponential growth. Exponential growth is an explosion growth. The explosion where something happens very flat and then has that moment where that critical point where the explosion just happens and then you grow up infinitely without bound. That's exponential growth, okay? It's explosive. The kind of growth we're going to talk about today is called logistic growth. Logistic growth is where you have exploding growth for a while, but then the growth just sort of peters out. It happens with stocks all the time. Like a stock will just take off and then it just eventually, it doesn't decline, it just sort of levels off and has a very flat rate of growth. We saw it with COVID. COVID grew crazy fast, the spread. You guys were maybe little, but I remember there were like websites that were counting. I'd log on Johns Hopkins, I'd look on their website and they were logging the number of cases. And you couldn't believe how fast. We'd never seen anything like that before, how fast it was growing and spreading. But thankfully, eventually, COVID leveled off. Okay, so that's what we're going to talk about today, our logistic growth and some of the real world applications and how does it in the world relate to calculus. So here we go. Here's exponential growth. Exponential growth comes from a calculus model. This is the calculus model right here. dp over dt is equal to kp. dp over dt is a rate. Okay, we should be very familiar with that. It's the rate of the population. Okay, so that's the rate of change. K is a constant. And P is the population itself. So exponential growth means that the rate is found by taking the population and multiplying it by a particular constant. That forms exponential growth. If you separate and integrate the model, well, let's look at separate. If we separate dp over dt equals kp, when we separate, we want all variables on the same side. So what variable do you see shows up more than once? P. All right, so we want to get all the P things on the same side. And so I would do that by dividing P. And I'd also need to move the dt to the other side. So what happens is I get dp divided by P, and I get K times T. That's the separation part. When you integrate this, I'm going to skip all the work of integrating. But remember that integrating gives us a, yeah.
Do you need the dt or is it just kt?
Yeah, I wrote T, I meant dt, thank you. When you integrate this, you get ln, absolute value P on one side, and you get kt plus a constant on the other. And then when you get P alone, tell me, how would I get rid of that ln? E, right. And so I'm going to have plus or minus, because of the absolute value, e to the kt plus a constant in parentheses up there. This is the exponential growth model. The population is either positive or negative. That means the growth can be either growing in a positive way, or it can be something that's called decay, where you go growing in a negative way, with that constant times t with an initial condition of plus c. This is modeled by this shape. Okay, that makes an exponential. Which has the explosion towards infinity. That's old. We have learned this already. You've known about exponential growth since probably at least Algebra 2. We are going to now look at something called logistic growth. Logistic growth is where it explodes quickly for a while, but then eventually levels off. We call that its ceiling. Okay, it sort of reaches its max and it won't go any higher than that. The difference, maybe just right here in your notes, put dp over dt equals kp. That was exponential. What's the difference? Compare the exponential one, that was the one from the previous slide, to this one. What's the difference? Because it still has this part that's the same. So what's different? The m minus p. It's multiplied by m minus p. It's multiplied by an additional factor. There's something else going on. There's an additional contributing factor that is making this no longer grow to infinity, but bend off. This is called logistic growth. So if you have it look like this without the m minus p, that will make exponential growth. If you have that same kp, but you add onto it the multiplying factor of m minus p, that will make something called logistic growth. And it will bend. M is what we call the maximum or the carrying capacity. All right, I am going to bubble circle that. Carrying capacity M, or M for maximum. M is going to be the level right here, where this would be an asymptote of how high the graph will get. It will never get higher than M. If you can figure out M, I mean, that was the whole COVID trick, was for scientists to see if they could figure out fast enough. It was a race against the virus. If we can figure out what is the maximum that this virus will go. The explosion, okay, you get a point right here. If you were to look at that with the eyes of a calculus student, a mathematician, that dot that I just put on there, if you're thinking, if you put your calculus glasses on, what happens at that point? Say it again, Grace. The concavity changes. That is the inflection point. Okay, and I remember scientists talking about we have to find the inflection point. If we can find the inflection point for this COVID virus, then it will start to slow down. But up until the inflection point, the virus was growing at an increasingly rapid rate. But if you could figure out the inflection point right here, I mean, this was real life calculus and real life math all coming into play. If you could, once we got to that, are we there yet? Are we at the inflection point? Are we going to finally start to see things slow down? And then once we got vaccines, then we could really see it slow down. So your job is to recognize the difference. So when you get a question like this, you should be able to say, oh, I recognize that as a logistic growth, just like you would recognize a quadratic. Oh, it has a square, I need the quadratic formula. Or, oh, it has, I recognize that as being an inverse tangent. You just recognize this as being in logistic growth form. So this is a population of bears set up in a wildlife preserve. They don't want the bears to grow exponentially. If the bears just kept growing and growing and growing, then the place would be overrun with bears and we would have too many bears. So, and there's just not enough space for all these bears. There's not enough food for all the bears. So we need to set a carrying capacity. So just based on looking at the equation, can you identify the carrying capacity? 100. Okay, so this place wants no more than 100 bears. I went to one of these wildlife preserves for bears this summer when I was in Alaska. It's rescue bears, but they're small and they can only handle no more than 7 bears at a time. They just don't have enough space. The bears needed more space, so they said that was their limit of how many they could have. Okay, next question. What is the bear population So find P for the population when the population is growing the fastest. Okay, what is the bear population when the population is growing the fastest? So the key in calculus is, what does growing the fastest mean? Okay, so yes, we are finding a maximum, but it's a question of, are we finding the maximum of the bears? We already know the maximum of the bears, right? We know the maximum of the bears is going to be 100. We want to find the maximum of the rate to answer part B. So part A, find max of the bears. We already did that. Part B, find the max of the rate, which is dp, dt. How do we find the maximum of something? Find its derivative. So I'm going to have to find the derivative of this expression, and then do what with it? Zach?
Find where it switches from positive to negative.
All right, great. So find the derivative of the derivative. So find the derivative of dp dt, and then find when that derivative changes from positive to negative. So we want to find d2p over dt. How would you approach finding the derivative of something that's in that form? Factor it out? It is factored. Okay, so distribute it out. So maybe distribute first. So take the 0.008 and multiply it by 100. So that's going to give you 0.8 p minus 0.008 p squared. I could do product rule, because this is one times the other. So you decide, is product rule it's kind of a personal preference? I'd probably distribute because I like to take the derivative of things like this better. All right, so Grace, what's the derivative of 0.8p? 0.8 minus the derivative of 0.008p squared is 0.016 p. And then Zach, what should I do with that? You said to find where it crosses from positive to negative.
Yeah.
How do I do that?
Graph.
Okay, or
Or you could find your critical point.
okay, which I do how? Finding the critical point by,
Setting it equal to
there we go. All right, so we want to set that equal to 0. So when we set that equal to 0, we end up with 0.8 equals 0.016p, and then we divide both sides. So p is a bunch of decimals, 0.8 divided by 0.016, and that'll be what p is equal to. So what is the bear population when the population is growing the fastest? So I start with the definition of what it means to grow the fastest, and now I'm able to find the population. Okay, so 0.8 divided by 0.016, what does that population turn out to be? 5. Okay, so P equals 5 bears. Is it 5? 50. I think you're missing a 0. I'm missing a decimal. All right, 50 bears. So the population is growing the fastest when we're at 50 bears. By the way, I want you to think about that being a logical answer. Go back to what we drew up here. If your max, we said, was 100, the graph is going to be growing the fastest when the graph is the steepest. And the steepest is also going to be where we have an inflection point. And that is where dp dt, the second derivative was set equal to 0. And so that is going to be 50. It's half of your carrying capacity. That always happens, is that the fastest rate is going to occur at half of your maximum carrying capacity. So that's a good thing to note for future. Fastest rate always happens at half m once you reach that value. That can save you on a multiple choice. If you don't have to show any work, you can like, boom, just go right to it if you know your logistic expressions. It's happening at halfway. Now we have the question, what is the rate of change when it is growing the fastest? So we found how many bears there are, but they want to know exactly how many bears per year this is when this is happening. So now we want what is the rate. So now we're going to go, we found the max of the bears, we found the max of the rate of the bears. Now we just want to find the rate. A lot of this is not going to be very hard math. It's just going to be reading and understanding what you're supposed to be finding. So we know dp dt is 0.008 times the population, which we now know to be 50, times 100 minus the population, which we know to be 50. So this is going to be 0.008 times 50 times 50. So I forget. 50 times 50 times 0.008, 20. But we need units on that. It's not 20 bears, or not just plain 20 bears. It's 20 bears per year. So at its fastest rate, this wildlife habitat is growing by 20 bears a year. Okay, so maybe there are 20 babies born that year, or maybe there are actually probably 25 babies born that year, but then 5 bears die, so you end up with a net of 20 bears per year. But understanding the question is going to pose, I think, the biggest challenge. Once you understand the question, you hopefully can do the math. We are not going to prove it, but to separate and integrate, okay, so we can get from here to here. This is the process of separate and integrate. Okay, so just as a reminder, I'll maybe put both of these things. If we start out with just KP, that's exponential. And if we separate and integrate that, we get P equals plus or minus E, let's deal with E to the KT plus C. That's exponential, separate and integrate. You should be able to prove that. That's baby cakes, separate and integrate. The other one, separate and integrate, requires partial fractions. We're not going to go through all of that. But the result is going to be this P equals M on the top over 1 plus A, which is a constant. It's not the plus C constant. It's a different constant, but it comes from the initial condition. And then MKT is the power on E. You should know where the M shows up in both places. In other words, you should know where M shows up in the differential form and where M shows up in the solved form. You should know where K shows up in both places. Those are going to be clues. Okay, knowing that K shows up out here, and then K is going to also show up here. The capital A is going to come from an initial condition. You'll be given on day 1, there are this many whatevers. So that will help you figure out what the A is going to be. It's like finding a plus C with an initial condition. All right, here's what I'm talking about. If you are given this equation for a population model, you should be able to write the population model. This is the population growth rate model. You should be able to write a plain old P model from that. So P is equal to, if I can figure out the carrying capacity, that will go on top. The bottom will be 1 plus the constant A, e to the negative, the carrying capacity, the K value, and T as a variable. So this one's set up pretty nicely for us. What is the carrying capacity? 100. So that would go up here. And then 1 plus A, e to the negative, and then I want M and K combined. So right now M is 100 and K is 0.0001. So we would want those two things combined, which is going to be 0.1 and then T. So that is our model for the growth rate of this particular whatever, we don't know what a population is. I can find my A with my initial condition population. So I was given the initial population is 10. So 10 is the value for P, but initial implies that I'm plugging something else in for something else. What am I plugging in for initial? Because I have to have a pair of numbers to plug in. Plugging in for 10 for P, what else am I plugging in? 0 for T. Okay, that's what initial means. Initial means that T has to be 0. No time has gone by. We're starting with 10. Okay, we are introducing 10 of something, 10 bacteria or 10 gerbils or 10 something into an environment where they are going to grow. So that we should be able to solve. So that means 10 for P, 100 is my numerator, 1 plus capital A, e to the negative 0.1 times 0. Yeah. Yep. Let's see if I can fix that. Yes. 0.01. Thankfully, times 0 doesn't really matter, does it? Okay, so then that's going to give me 10 equals 100 over 1 plus A, because e to the 0 is 1. Mathematically, how do we solve for A? I'd cross multiply. So I'd put a 1 under the 10. And I would cross multiply. And when I cross multiply and solve, I find out that A is 9. So then I can write an official final growth model. I could say my growth model answer is going to be P equals 100 for M, 1 plus 9 for A, e to the negative 0.01 T. And that is the growth model that represents this particular situation. The initial number of the population was 10. That helped me figure out that A was 9. The growth model started with has 100 as its carrying capacity, and its growth rate is 0.0001. Was it pretty easy to find the 100? Okay, so our last example is it's a little more challenging. All right, it's not as easy to find the 100 here because it's not in the format that's factored. Remember when Grace suggested in a prior problem to distribute? This problem's been distributed. We need to undo that. It's going to be easier for us if we can get it into this form. We want it to be minus p. Right now, it's not minus p. It's minus 0.0004 p squared. So I want to get this written in the model where dp over dt has a k and a p and an m and then a minus p. So I need to factor this. So what do I need to pull away from that last p squared term? I need to pull away a p, so it gets down from p squared to p. What else should I be able to pull away? The 0.0004. So I'm going to do that by division. So dp dt is going to be 0.0004p on the outside. That's going to leave me with minus p on the inside, but it's also going to change the first term, the 0.01p. Here we're factoring. We're pulling it out. You just go back to like basic, math. If you had 28x minus 49x squared, and I said to factor that, you would pull out 7x. And then to figure out what was left, you would divide 28 by 7x, and you would divide this by 7x, and that would tell you, oh, you're left with 4 minus 7x. Okay, you divide. So we're going to do the same thing here. If we're pulling out the 0.004p, we're going to divide by 0.0004p, and we're going to divide this one by 0.0004p. So that will reduce. It will reduce the p's and it will reduce the 0.4s, leaving me with just p. That's how I know it's minus p. And the other, the p's reduce completely, and then I need 0.1 divided by 0.0004, which gives me 250. Once you do that, it's like, oh, now I know what m is. I can easily, clearly see that m is going to be 250. What else is easy to see?
K.
Yep, k is going to be 0.004. And so my model becomes p equals the 250 in the numerator, 1 plus a, and then e to the negative mk. So this will be negative, and then 250 times 0.0004, which is 0.1 t. So now I have everything but the a. How do I find that? Plug in 28 for p and 0 for the time. So 28 is going to go in for p, 250 over 1 plus a when I plugged in 0 for the time. We will cross multiply. Okay, put a 1 under the 28. Cross multiply. That'll give me 28 plus 28a equals 250. So we subtract 28 and divide by 28. So a turns out to be not a nice number this time, but 7.929. So then I can write my official final statement. So my P is 250 on top, 1 plus 7.929 e to the negative 0.1 times time. That is the logistic growth model for this particular population that's going to grow to a cap or a carrying capacity of 250. All right, so the final question. When is the population growing the fastest? Well, I told you how much population that would be when that happens. Okay, when is it growing the fastest? At half of m. So when it gets to how many in the population? When it gets to 125. Does that answer the when? No, it tells us how many, but it doesn't answer the when. So we know it will happen when it gets to 125. That's half of its carrying capacity. So then we can solve by setting that equal to 125 and solving that mathematically. You can do that a couple ways. You can graph this, and you can see that you could see the graph that goes up like this and gets to 250. So it's going to get up to 250. You could throw a graph on that's going to cross at 125. Y equals 125. And you could do a calculate intersect on your calculator. That would work. Mathematically, you could cross multiply. So I could drop a 1 under the 125. And I can do some mad skills algebra and doing cross multiply that way. Personally, I probably would prefer to do the graph because I'll let the calculator do it for me and find that intersection point. So you have your pros and cons. Okay, if you do it algebraically, you just have to be confident in your cross multiplication skills, which isn't bad. You can cross multiply, do a little adding, do a little subtracting, do a little dividing, and then ultimately do a natural log. With the graph, I feel like the downside would be A, not being able to come up with your window. That could be a problem. B, it could be making a mistake when you type in the actual 250. You could forget a parenthesis or something, and that could throw you off. So either one of those are your downfalls. I'm going to stop the recording, and I would like you to pick one of those. I'd like you either to decide I'd like to do the algebra way, or I'd like to do the graph and calculator way, and come up with your time. Yeah.
So for every logistic model problem, if we're trying to find when the population is growing the fastest, it's always like when the population is at half of the carrying capacity.
Mm-hmm.
That's like just true
Mm-hmm.
for every single.
Mm-hmm. So we get the solution that this happens at time 20.705. Now we don't have a unit on time, so we don't know if this is days or months or years or weeks, but that is the amount of time where this population would be growing the fastest.